Well, great, everybody. So thanks for coming along. I've got a lot to tell you. It's a passionate area of mine, and I'm going to try and push through pretty quickly. Right, but I think in order to really set the scene for the main speakers, Pascaline, Alice and Oksana, I really need to sort of lay some groundwork. I'll give you some past reference background on where the technology is, what we're doing, and a brief snapshot of a broad area of applications, just to, bearing in mind that the audience is also fairly broad in their interests. So today I'll take you through an outline of the limitations of current FTIR or current infrared. I'll take you through how O-PTIR works and all that it provides, and then I'll give you a brief snapshot of applications, and then we'll pass over to our main speakers today. Okay, so most of you would be familiar with FTIR, which is a type of infrared spectroscopy. But it is a fairly mature technique. It's been around for a while, and I believe it's reached sort of technological limits. That really means limited spatial resolution, and that really stems from the fact that we're dealing with long wavelengths, and naturally our spatial resolution is limited. Often complex sample prep. Most things work best in transmission mode, but to cut things, it's difficult to impossible. That can be mitigated to some extent with ATR, but of course that requires intimate contact. It requires a precise targeting. Things can move. You can damage the crystal. You can damage the sample. And here's an example of an ATR tip creating many indentations along the sample. So if you can avoid touching things, it's always best. But I think one of the underappreciated issues with current day FTIR are these sort of so-called dispersive and scatter artifacts. So an ideal spectrum is measured in transmission, and that gives you, imagine this is a thin polymer film, PMMA, you end up with a beautiful spectrum, nice flat baseline, nice symmetric peaks. But if you take the exact same material and make it a 15 micron bead and measure that in transmission mode, well, the spectrum now looks very different. Make it a different size bead and make it smaller yet again, the spectra changes. Baseline, peak shift, peak split, it becomes a real mess. So the spectra are very much particle shape and size dependent, and also surface topology as well. So that, of course, makes interpreting and searching your spectra very difficult. So that's kind of on the IR. On the Raman side, Raman's perhaps less technologically mature. There's a lot of advances still happening in Raman, but there are still some very important fundamental limits. And any of you here that are Raman practitioners will probably feel the pain when I talk about it. So probably first and foremost would be autofluorescence. And that is perhaps by far the #1 issue with Raman. Most samples, or many samples, depending on sample type, and especially biologicals, can have significant fluorescence, and that often swamps the signal. Maybe you can subtract it out, otherwise process it, and sometimes it can be really destructive. Sure, you can move to longer wavelengths to mitigate some of that, but that also comes with a massive drop in sensitivity. And that comes on top of an already limited sensitivity, just because of the Raman cross-section is much, much smaller than that for the IR. When you're doing imaging in Raman, you always have to collect hyperspectrally. So it's point-by-point mapping, and you can't do single frequency imaging, which is something I'll get to in a minute. For anyone doing live cell work, phototoxicity can be an issue. Often many milliwatts, many tens of milliwatts even, of laser power needs to be used to overcome the sensitivity issues, but that can be quite toxic to samples, to living samples. Raman spectra can also be dependent on the excitation wavelength, especially if you start hitting some resonances. Right, so the number of issues there as well. All of those really are overcome with our technique, the optical photothermal infrared technique. It's a pump probe technique where the pump is an infrared laser and the probe is a short wavelength visible laser, typically a green, but can also be a near IR laser. It provides a submicron resolution, spatial resolution. So it's very much like a Raman microscope. In fact, it's much more like a Raman microscope than it is an infrared microscope in terms of what it does, how it operates. But the big difference is, of course, it gives you infrared information, as well as Raman. It gives you FTIR-like data, transmission-like data, but it's collected in reflection mode. So none of those distortions or artifacts, and I think we already said it's non-contact. So how does this almost seemingly miraculous technique work? Well, we start off with a tunable infrared source, a QCL. You've probably heard about those. And that is shone through a Cassegrain or a reflective objective onto the sample. Of course, being infrared is a fairly broad spot. At the same time, collinearly, we shine through our probe beam, typically a green. Being a short wavelength laser, we can focus that down really tightly, down to about 0.5 micron in the green case. And as we tune our infrared wavelengths, let me go back to this. So as we tune the infrared wavelengths, we synchronously monitor the green while we're tuning the IR source, right? And that creates an infrared spectrum. It becomes almost a pure absorbance spectrum, right? And that's collected typically in under a second or about a second. And because it's a QCL, we can actually park the laser at any wavelength, any wave number, and then create these discrete frequency or single frequency images, in addition to hyperspectral scans as well. And these single frequency images can be actually really, really useful. Here I attempt to compare and contrast traditional IR and Raman against a range of what I think are key attributes. So if you cared about spatial resolution, you'll probably want to be using Raman, not infrared. If you cared about fluorescence interference, you'd probably be steering clear of Raman. If sensitivity was an issue, IR, it would be probably, I mean, these are broad generalizations, of course, but it would be your choice. Hence, speed of measurement is also typically better with IR. When it comes to libraries and the extensiveness of the libraries and how interpretable or how rich your spectra are, infrared wins hands down. There's about 10 times more infrared libraries than there are Raman libraries. If you want to work in reflection mode, which is generally a preferred mode, Raman is great for that. FTIR doesn't work so well in reflection. Water vapor can be troublesome in IR, not so much in Raman. Water solvent, again, typically not so good with IR, fine with Raman, and so on. And also the spatial resolution independent of wavelength. So in the IR, typically your wavelength, your spatial resolution is very much dependent on your wavelength. In Raman, it's fixed. So if you look at that, it's no surprise that most labs have one of each, depending on what you want to get out of your experiment, what your needs are. You may go to Raman, you may go to FTIR. Worst case scenario, you may have to use both, in which case you're taking the sample from one to the other, and good luck in finding that same 1 micron spot. But what we do with O-PTIR, and this is of course my favorite animation, is we take all the best attributes and put that into a single platform. I mean, it's more than a graphic, it's actually quite literally the case. Right, now we've been around for about 2.5 years, well, probably more like 3 now, and there have recently been some new developments, so I'll take you through those very quickly. So our infrared, so it all starts with the QCL, or with the infrared laser, the pump source. And traditionally, well, currently the standard QCL covers down to about 950, so 1800 to 950, it's a 3-chip QCL. And if you have strong interest in the high wave number region, we can also offer a second OPO laser. But perhaps what excites me the most are these new custom QCL options that are coming onto the market. And my favorite of all time would have to be this CH chip, what I'm calling a CH chip. So when we couple that into our standard QCL, this becomes the 4th chip. You end up with a dual range QCL that covers the CH region and the majority of your fingerprint region. So that at the moment is my favorite laser. Of course, there are some who are interested in the silent region, those doing CD stretches or interested in nitriles or infrared tagging. We can do a combined silent region fingerprint, or if you want the access to the low wave number down to about 800, we can do a wide range QCL that covers that range there. When it comes to the probe, which of course doubles as your excitation laser, the 532 is the standard. We can offer a 785. And that's fine, well, not fine, it's good for anything that's sort of dark or easily burnt, things that are perhaps a reddish or orange in color, that would absorb a lot of the green. Or if you care about fluorescence on the Raman channel, you can opt for the 785. So I'm going to take you through some examples of some data collected off this new CH fingerprint QCL. So all of this data has been collected in reflection mode. These are about 5-second collection times from about 0.5 micron spot. So the FTIR reference are all transmission data taken off films that are about 10 microns. The O-PTIR data you're about to see is taken off a thick block of polymer collected in reflection mode. Right, so that's polypropylene. Again, in red, we have FTIR, and black, we have the O-PTIR. So you can see that's almost a perfect match. There's no daylight between those two curves. Polyethylene, the same, PET, nylon, and polystyrene. So it's actually phenomenal how good the two techniques match. So which just means that anything you've got already with FTIR, be it commercial libraries, be it data that you've collected yourself, it's fully equivalent and comparable to anything you collect on O-PTIR. I'll talk a lot about spatial resolution, and I think it's important to understand where spatial resolution comes from, or how we calculate all the variables that contribute to it. So Rayleigh criterion is a good approximation for that. It's pretty simple. It says it's wavelength really divided by numerical aperture, and because with regular IR your wavelengths are quite variable, all the way from your long to perhaps a little bit less than long. If you were to plot that, you see a curve like this. Remember, the smaller numbers are better in this case. So when you're here in the fingerprint region, which is the most information rich, that's where your spatial resolution is worst. At 1,000 wave numbers, it could be as bad as 12 microns. With the O-PTIR technique, because we use a fixed wavelength probe laser together with a high numerical aperture, our resolution is under 500 nanometers, and importantly, it's fixed across the entire wavelength, which means compared to an FTIR system, it's about 30x better at 1,000 wave numbers. Right? But perhaps the most exciting element to what we do is this combination of these techniques, the sort of simultaneous infrared and Raman that we're doing. So it's the same spot, same resolution, same time measurements. And how that works is we take our pump beam, our infrared, and shine that into our Cassegrain, as I've said before. The green or probe beam is also collinearly sent through the Cassegrain. Our Photothermal Magic happens on the sample. The reflected green comes back to a visible detector. That's also an important point. It's a visible detector, so there's no liquid nitrogen cooling anywhere. But any of the Raman scattered photons, remember, there's always Raman scattering happening, whether we like it or not, whether we want to use it or not. The photons are being scattered via the Raman effect. And in this case, we're simply taking advantage of that using a dichroic filter to send those to a Raman spectrometer, and the unscattered, or the Rayleigh light, goes straight through to your visible detector. And this way, you very, very efficiently collect only the Raman photons, and all the other photons go off for infrared signal extraction. And this takes advantage of the complementarity of infrared and Raman. I think we've been taught that for a long time. The IR can confirm the Raman results, the Raman can confirm the IR results, and it's also the one instrument, so you don't have to move samples from one to the other. Okay, if I'm going okay for time, I'm going to take you through a few application examples. I won't go into too much depth because our guest speakers will do most of that. But like with FTIR, like with Raman, the application fields are extremely broad. That's good for us, but also presents some challenges because it's, well, where do you target, where do you go? For us, it's been very much life sciences, and that's also reflected by our speaker list today, but things like microplastics, polymers, there are some really cool pharmaceutical type applications. Failure analysis in the electronics industries have also worked out really quite well for us. Anyone following the literature in the O-PTIR space, you will hopefully have noticed that there are a lot of publications coming out. Starting off from 0 a couple of years ago, last year we hit about 14. By the end of this year, I expect to be somewhere between 30 and 40. And I know that there are several papers that are just, that are almost about to come out, and perhaps another dozen more that are in preparation. So that's really reassuring, pleasing, and exciting for us in this field. I won't steal Oksana's thunder, but she had an early paper in a really high impact factor journal. And that's being cited like crazy at the moment. So I was lucky enough to play a small part in that. But she'll take you through how even across very small spatial resolution points, we were able to see differences in protein secondary structures. Right. Publication on polymers here. This is the one where we use infrared and Raman to look across an interface of a PHA PLA laminates, and there was interest here in this interface or this mixing zone. I'll go through this very quickly, but these are the spectra. Each of these spectra are 100 nanometers apart, and in the paper they applied 2D correlation spectroscopy to further extract out some meaningful mechanisms in how the samples interact. A classical laminate example. Here we can see easily something that's 1.6 microns, and 1.6 for us is relatively easy. Glass contamination, surface contamination on glass. That's usually a difficult or a challenge for a regular IR system, but here we can see strong organic peaks overlaid on top of a bit of a glass hump, which you will get whenever you measure on glass. But glass isn't totally opaque like it is in a regular IR measurement. And we've been able to focus on some of these key peaks and do discrete frequency imaging. You can see how these different regions light up based on where these various contaminations are. It's all in reflection mode. These are some. This is in fact from Seagate. So this is a company that makes a lot of hard disks. You may have one in your laptop, and there they care about these minute defects. Anything, they're looking for smaller and smaller and thinner things these days. But they've been thrilled. They're internally telling us that they're getting over what they believe to be 90% success in identifying the unknowns, and they're even able to see things as thin as about 60 nanometers, all with an optical far field technique. Here's a nice proof of concept type of measurement. These are sort of 900 nanometer polystyrene beads. That, I believe, works out to be about 500 picograms, if my maths is right. But we've measured on and off a polystyrene bead. And off, you get a flat baseline, which is just from the calcium fluoride, but on the beads, you get clearly polystyrene spectra. And these we're measuring here in the infrared, optically far field reflection mode. All right, if anyone's tried to measure anything on fiber before with an FTIR and reflection mode, you'll know that it doesn't work at all. Not that it's poor, it just doesn't work. In this case, we've measured surface coatings on a PET fiber with additives, and you can see along the length of it, our additive peaks are changing, and these are all raw spectra. These are the spectra that you get straight out of the instrument. And the spectra are diameter independent, whether it's a 20 micron or an 800 nanometer nanofiber, the spectra still look like spectra. Okay. Phase dispersion, so I'll quickly move along to that. So this is a fairly coarse image. It's funny how when I say that 500 nanometers now for me is a fairly coarse image. If we zoom into that, things get really quite interesting. At 100 nanometer steps, we see some remarkably small features. But firstly, here's some spectra on and off these hotspots, and we're using these two peaks, the ratio of those two peaks to drive our contrast. If I skip through very quickly, some of these are as small as about 275 nanometers. Some of these inclusions. Right. I won't. So this is going to be more of Alice's thunder here, so I won't steal too much of it. But this is one of my early live or hydrated cheek cell measurements. Having taking a swab of my cheek, putting on a calcium fluoride, a drop of water, and a cover slip on top. Taking some random spectra around the cell, and unfortunately I actually forgot to take a visible image for this one, but I quickly saw that there was some spectra that had a clear lipid, some had a clear what I thought was probably a nucleic acid peak. So then taking advantage of the QCL, tuning to those particular frequencies, doing single frequency imaging and generating an RGB overlay, I ended up with what I thought was a pretty stunning image. It looked like almost a fluorescence image. So you can see nucleus, obviously in the middle, and some lipid inclusions throughout. But again, it's important to stress these are measured in water. There's no water correction here. So what you're seeing here, in fact, is a water peak, under which there will always be a MID1 peak. This is a little bit of what Pascaline's group is doing, so I won't talk too much about that, but one of the earliest work I did with one of her team members is looking at breast tissue calcifications with FTIR. It looked like a broad area of calcification. When we went in there with the O-PTIR, tuning it at 1050, the tiny little calcifications lit up like a Christmas tree. Some of these are, in fact, there's a spectra on and off. But some of these are 5 microns, some of these are under 1 micron. So it's no surprise that at 1,000 wave numbers, FTIR can't see this. Because with FTIR, you're probably at 10, 11, 12 microns of resolution, and you won't be able to see any of this. I'm going to skip through these quickly because I know there's time pressures. Microplastics is perhaps the other emerging field. In fact, probably more than emerging, it's emerged. Well and truly a science in itself these days. But microplastics, I think it's a great technique because it brings together the infrared and the Raman, because there are many groups who swear that Raman is better and others who say, no, FTIR is better. And by bringing these two techniques together, I think we're taking the best of both of those. So here's a nice example of polystyrene beads of various sizes, anywhere from 900 nanometers up to about 10 microns, and a PMMA in there as well for good measure. And we've then mixed it with salt water, with salt, and dried it. So now we have a mixture of beads, we have a mixture of salt. If anyone's tried to measure particles in the presence of salt crystals with an FTIR, you'll know that it doesn't work. The salt will scale like crazy and you'll get nothing. With O-PTIR, you only get a signal when you have an absorbance. And that's the beauty of it, which makes it really immune to the presence of non-absorbing but scattering particles like salt crystals. So here we can see the salt, there's a big salt crystal there, there's a particle next to it. These are all the polystyrene particles from the different sizes. These are the PS spectra, the PMMA spectra. Again, the spectra are consistent regardless of particle shape or size. Right, in this fairly simple binary mixture, there are two clear peaks, so we can then tune the laser to those two peaks, and then the particles light up. Okay? Again, independent of particle shape or size. Right. Another really cool feature is because we can do the simultaneous IR Raman collection, we can also do the simultaneous IR and Raman spectral searching in partnership with the Know-It-All software package, which is now owned by the Wiley company. So with those, we can actually search simultaneously the IR and the Raman and present the result of the 2D scatter plot. So on the x-axis, we've got infrared spectral hit quality index. On the y-axis, we've got the Raman spectral quality index. And so the best matches are going to be in the upper right-hand quadrant, which means it's a good IR and it's a good Raman match. Okay. And I threw this one in because I know there's a few people here from the pharma industry. I see huge potential here for subvisibles analysis for biopharma folks. And with everything that's happening in the world and with all the vaccines that are coming out, in quality control and making sure that you know what those particles are and hence be able to remove the cause of those is going to be increasingly important. So here's really a model of a biopharma subvisible subanalysis. These were measured on gold-coated polycarbonate filters. This, in this case, is a relatively large gelatin particle, in that with what looks like a perfect protein spectrum. The same sort of analysis on gold-coated. This is now a black particle, some unknown, it wasn't known. So this is a simultaneous infrared and Raman collection. If you then search it against the library, well, you can be pretty sure if they're both matching really well, you can be really sure that in this case it is actually polycarbonate. I may skip this one. This is a publication from Kathy Goff. This is one of my favorites. In fact, I've got this same sample loaded in the system in Santa Barbara for the demo at the end of it. It's really cool because we looked at cell differentiation on regular glass slides. That's right. So we measured these on glass, not calcium fluoride. In fact, the publication is it's being reviewed, and hopefully it'll be out soon. But those spectra are single scans co-ed, so there's about one scan in those, about a second, half a micron spot on glass. And that's also using the CH laser. Right. And then I also did some ratio imaging, looking at the CH2 to CH3. So these images tell us a little bit about chain length and the distribution of chain length. And if you then ratio CH2 to the protein peak, it also gives you an idea about protein to lipid ratios. Right. So if you look at those images, they're perhaps what you're used to seeing with Raman microscopy, but you've got that richness that you get with infrared, and especially when you're interested in proteins, because the infrared is so much more sensitive in proteins. This is a isotopically labeled bacterial study out of University of Liverpool, where they looked at carbon-13 and N15 labeling of E. coli to work out some metabolism pathways. And again, O-PTIR excels being able to obtain single spectra from single cells, single bacterial cells, which are in the order of about a micron. This is one of their, it's not from the paper, but it's a sample from that same group. In fact, this is now using a CD chip, or the silent region chip, so you can actually see some carbon deuterium absorption within an E. coli. So that's an image at 50 nanometer steps of a single bacterium. And I've got now spectra along the length of the bacterium. In fact, I should have zoomed in, but there are some subtle peak shifts within that. So I was pretty excited when I got that. This same sample now with infrared and Raman. In fact, I'll be showing you some live measurements on that at the end of this on some bacterial spore samples that I've got. So I've come to the end. That's pretty quick. I'm pretty tired. But so what I want you to remember is that we've really combined the best of both technologies into a single platform. The submicron, so you see more information. It's non-contact. It's reflection mode. There are no dispersive artifacts, even though you're working in reflection mode. So the parts of the spectra are completely particle shape and size independent. Sample prep's easy. Lots of new QCL options, broadening out the spectral range. And I didn't touch on this, but I want to sort of throw it out there a little bit, is we're now also looking at combining fluorescence onto the same microscope. So ever think about that as well? Could you imagine also imaging your samples with fluorescently labeled, and then using the fluorescently labeled image to guide you where to collect your infrared spectra from? Right, so watch this space. And yes, IR plus Raman, same spot, same time, same resolution. How'd I go for timing, guys?
Thank you, Mustafa. I think that's well. There was a good question that I think is very important also for the presentations and demonstration. What is the penetration depth for this technique?
Yeah, given how often I'm asked that question, I really should actually include that in my slide deck. It's one of these questions that I'm going to answer by saying it depends. It depends on what the material is. You can imagine if you have something like polyethylene, which has, which is mostly transparent in infrared, well, that infrared beam is going to go down many microns, if not 10 microns plus. But in practice, for most organics that have lots of absorbances, we say it's generally a few microns would be the depth of penetration.
Excellent. We have another question as well. So just checking that person got it correctly. So there is an IR amplitude modulation of the visible lights via sample, and the gain in spatial resolution is through the smaller visible interaction volume and high spatial IR absorbance within the sample. If so, the resolution should be still dependent on the IR absorbance, right? Is this the case?
No, the spatial resolution is only governed by the probe beam in this case, which is the 532. So you have, it's a pulse beam that goes on and off very quickly. Now there is a dependency, or there is a sort of connection to spatial resolution with the pulse rate of the QCL. If you pulse slowly, the heat will diffuse, and that will kind of blur the spatial resolution signal a little bit. So we pulse this at around 100 kilohertz, which keeps that the diffusion length short enough so that it doesn't become a limiting factor in the spatial resolution, which means you get what the green light in theory can provide.